Saman. I'm going to be teaching a class this fall called Our Moon, and I was going to use that as an outline for this talk. I'm not going to talk about all these topics, but the course will. I want to briefly show how geopolitics and law might be related. Look at the flags that have the moon. Typically don't want to show flags in this way. It's disrespectful putting them in this hierarchical structure. There's no way to show them on a screen without doing this, so it's alphabetized. There's 20 flags here, all having the moon, mostly in crescents, mostly to represent Islam. How is the moon related to a lot of other things, not just science and engineering, which is the typical thing that we look at for this talk. I'm going to focus on science. I want to talk about things that we've discovered by the Apollo program. One of the neat things was discovering special types of rock on the lunar surface. This is one of the famous examples called the Genesis rock. It's a northacitic rock. My background is not in geochemistry, so I remind myself what that means. It's made out of essentially one mineral, plagioclase, and you can see 99% of this rock is just one mineral, which is rather strange because if you go out and pick up the rock, it's typically made out of many minerals. That was Apollo 15. It was actually discovered as part of the Apollo 11's sample collection. As we celebrate 50 years of Apollo 11, we also celebrate this idea of lunar magma ocean that came out of these samples. This idea that most of the moon was molten at some point, and that came from these samples, Apollo 11 fragments of the north side that were discovered. The moon was mostly molten in the past 4.5 billion years ago. There was a lunar magma ocean that covered the moon, perhaps all the way through. Maybe most of the moon was molten rock. It solidified in stages. The first stage was rather rapid. It went from a mostly molten moon to a mostly solidified moon in probably 10,000 years or so, very quickly. And what's happening here is that minerals are crystallizing. They're more dense than the liquid they're in, so they sink to the bottom, so the moon solidifies from inside out. This is solid material that is increasing over time, so the moon is cooling from inside out. After about 80% of the moon has solidified, mineral plagioclase becomes stable. It forms rocks, north sides that are less dense than the liquid it's in, so it floats to the surface, forming this flotation crust or thermal lid that slows everything down tremendously. What was mostly a radiation issue, it's heat to the fore, it's getting rid of energy rather quickly. Now, once you have this thermal lid, the blanket on top, it tremendously slows down this cooling process because it's now a conduction limited problem. What used to take 10,000 years or so to get to mostly solidified, the next step would take 10 million or 100 million years. So it's significantly slow. So that's overall how the magma ocean solidified. That made it seem very simple, but there's a lot of detail that goes in it. So this is supposed to show a little bit more of the detailed process of what the magma ocean cooling is like. There's convection going on, tidal heating, effects due to impacts, which I'll talk about in a second, geochemistry and crystallization sequence, and so on. Part of my PhD work was to look at how impacts affected the cooling of the moon. We looked at the fact that once you form this conductive lid, if you puncture through that lid, you'd speed up the cooling process, and that's what we looked at here. We did it in a simple way because this process is very complicated. It depends on the impactor size, the velocity, the crustal thickness, and it's a time-dependent problem. So there's a lot of factors. What we did was we parameterized it. We knew how much material was hitting the moon, and then we figured out an area of these holes that were on the moon. This K is somewhat like a resistance. The higher it is, the smaller area of holes that are produced on the moon. In the case where K is smaller, you have more surface area of the moon covered with holes. If there are no impacts, you expect the magma ocean to crystallize about 30 million years. And we'll ignore kinetic energy for a minute and look at the case where if the impacts come and just only punctured through the crust, what would it do? And as you'd expect, the more surface area the moon has with holes in them, the cooling process is faster. So what used to take 30 million years would take 5. Ignoring kinetic energy of the impactors is not ideal, but it's one of those things we don't know how much of the kinetic energy of the impactors are being converted into thermal energy. It's either nothing or everything. It's either 0 or 1. In the case of these orange diamonds, is if all of the kinetic energy of the impactors converted into thermal energy and heating the magma ocean. In that case, even if there are very few holes on the surface, you'd expect the magma ocean to take longer to crystallize than in the case of there being no impacts whatsoever. There's a point where the balance, 10 to the 7 K value, is that you have impacts, they're puncturing through the crust, but they're delivering enough thermal energy where they balance. It's as if this impact process is not happening at all. Second part we're working on is to look at the impact process in a little more detail. We're using a hydric code called ISAIL, and what you'll see when I play the movie is on the right-hand side it's plotting temperature, on the left-hand side it's plotting damage, which is a measure of total strain. So a damage of 1 means that strain beyond its own length. That's what damage is. So I'll play the movie. It's a little distorted because it's actually much longer than the screen. You'll see typical impact process, except the fact that it looks more like dropping a rock into water. There's a lot of sloshing because this red is magma. Typically, when you're looking at impacts, you're not hitting a surface that has a liquid Europa, for example. You might have a solid surface and a liquid just beneath. So you'd see a lot more sloshing than it was just a solid object that you're hitting. That's ongoing work. But for this talk, I thought it would be more interesting to talk about the chemistry because I don't know that much about it, and you probably did. You might wonder, be skeptical, hey look, you picked up a few rocks on the moon and you're claiming that the entire moon essentially was molten at some point. More evidence beyond that, you can look at the surface of the moon. That's the near side, far side is on your left and your right. The white dots are showing cases where the north side is most pure and the red is olivine-rich material. The point here that this paper was trying to make is that there's a global layer of the north side on the moon. This is material that's been excavated by impacts. Europium likes to be with the north side. So if you look at the crust, you see increase in europium content versus the salts of the moon, representing the mantle where europium seems to be depleted. Europium substitutes for calcium. That's why there's this enhancement of the crust. This is one of the clues for the moon to be molten. The other is using compatible elements. The stuff that didn't go into any of the minerals seems to have just concentrated itself mostly on the near side, the dark spots, the men on the moon. That's a result of the magma ocean crystallizing, and the very last bits of it, PREEP stands for potassium, rare earth elements, and phosphorus. These elements weren't going into other minerals, were concentrated and then brought to the surface through volcanism. This is my who cares slide. Why does it matter if the moon cooled in 10 million years or 100? This is a timeline of the early moon. Dotted black line is plotting the oldest CAIs, this material in the solar system, 4.567 billion years. There's a range of when the moon would have formed. This is the earliest point where the moon could have formed and the latest point. I've added in this lighter box to represent about 30 million years that would take to solidify the moon. The moon forms, it takes so much time to cool, then it's solidified at this point or this point. That's one way to look at it. The other way is to look at the samples that we were talking about before, the Apollo samples. The oldest sample is as old as the solar system, which is obviously not right. You have also a younger sample. This spans about 270 million years. One way to just blindly trust that is to say, okay, the moon formed and took 270 million years to solidify, because the oldest material should float to the surface, the youngest material should be at the bottom of the crust, and that difference should be shown by the samples. But we know that samples can be reset by impacts. There's evidence that some of these samples have already been shown to have reset. So we can't really blindly trust just the absolute age ranges of the samples. Recently, people have looked at, can you grade these samples and look at just the samples that have multiple chronometers, there's little scatter on the isochron plots, etc. So there's 5 grading criteria that they use. There's one, a north side sample that meets all the 5 criteria, and that creep layer, the last remnants of the magma ocean. What's the age of that? Creep, meaning original. They're all about the same time, so that's good. Some sort of consistency there. But we have no constraint of exactly when did the oldest lunar crust form. We don't know. It's not surprising because impacts could have moved them around. Plus, you have to consider the fact that the Apollo astronauts wouldn't have sampled the crust all the way through. It's 40 kilometers or so. There's a regolith, there's some mixing, but it's unlikely the whole crust was samples. This shows why understanding how long the moon took to solidify is important, because that's T0 for geology. The other thing to consider, about 90% of the way, once it's crystallized, the magma ocean starts forming ilmenite. It has this really strange density structure inside the moon where there's an increase in density at the very top. Naturally, that stuff wants to go down. We're here modeling how this layer sinks to the bottom, the ilmenite-bearing layers, which start at the edge and then they sink in over time. If you look at Apollo seismic data, people have estimated the current density structure of the moon. The blue and the orange are showing the various estimates. When you model the evolution of the magma ocean, what is the resulting density profile after the overturn? They don't match. There's something going on here. They're not in agreement. This is not the density structure before overturn. This is after. They're not in agreement. So that's more reason to look at this in detail. Typically, how the magma ocean is modeled is you have to estimate what the initial chemistry was in the magma ocean. I've listed several compositions, but they generally fall into two camps. Start with Earth's mantle composition and adjust it. Either there's more refractory elements or about the same as the Earth. There are two camps that these compositions fall under generally, so I just picked 7 just to give you an idea. Once you pick your composition, to decide what are the minerals that will crystallize and in what sequence based on experiments. Once you have this assemblage that you've decided should be what happened in the magma ocean, then you build a thermal model on top of that. These are the steps that are currently used to do this. What I'm trying to work on now, trying is the key word, is a new way of doing this. This could be generalized. We can start with a composition, give it a depth, give it a temperature, and then have a code that will produce a mineral assemblage based on a geochemical model, and then give you a crystallization time. There are a few features I'd like this to do. It's a work in progress. Take the magma ocean, divide it up into several layers, have each layer track its own composition, reduce the temperature of one layer, it produces a certain mineral, you have to track how that mineral evolves. Maybe it forms in this layer, but it's too dense for that layer, so it'll sink. So you'd have to track the composition within each layer. In increments, you would crystallize the entire magma ocean, it would produce its own mineral assemblage, and then give you a crystallization time. Since I don't have it working yet, I want to show this as a demonstration of the idea. This is the same 7 different compositions from before. This is taking a little parcel of magma of these compositions, taking it from 1700 Kelvin, dropping it down 10 Kelvin, looking at how much energy is being released. What I'm trying to show here is that the amount of energy released in this process varies from composition to composition. So what does that mean in terms of cooling the moon? If your quantity of energy you're trying to get rid of is varying by the composition, the cooling time would vary based on the composition as well. In this particular case, the higher MgO number produces more energy. To look at it a little bit more detail, taking a parcel of magma from 1700 to just below 1300 Kelvin, 7 different compositions for the 7 different colors. What this produces is not surprising. The olivines and the pyroxenes is what you'd expect for a magma of this composition. What is interesting is that when olivine forms is different for the different compositions. So when meaning what temperature at which olivine forms is different for the different compositions, as well as, like I said before, the energy that's released is dependent on the composition itself. Still forms olivine, but at different times and with different energy. So you might go, well, maybe this averages out, but for that previous plot, taking it through from 1700 to 1300 Kelvin, this is the total amount of energy that was released for each composition. The total varies, not by order of magnitude, but by some factors. So this is the flow chart. I can come back to this if people are interested, but I want to put it up there in case anyone's interested in looking at the details of how this code will be set up. The key is if solids form. It's constantly asking a geochemical model if a certain mineral is stable at this point in pressure and temperature. If it is, it has to deal with that. Where do you put it? Which layer is it neutrally buoyant in? And then how much energy is released in the process.
So another discriminant, right, is the composition of them. So you have all the different models.
Yeah.
And you have olivines coming out at different temperatures.
Yeah.
And they must have distinctly different magnesium ion ratios, for example. Is that something you've been able to look at yet? Or
I haven't looked at that yet, but yeah.
That would be an additional discriminant because you want to get to a certain olivine composition that's found in the rocks. Right?
I see.
It does treat the solid solution of olivine from post-derived.
I'm not sure I understand.
I'm just checking that the model includes the variability of olivine composition in terms of magnesium.
I think so, but we can chat
I
maybe.
almost certainly would.
Sorry?
I almost certainly would.
So is this going to change anything? You had that model comparison with what was deduced from, I guess, radar data or whatever, where there was a discrepancy.
With the density
With
structure?
with the density
Yeah, I
structure.
don't know what that
Does this have
derives.
anything in it that's going to,
Um,
that can address that?
Instead of imposing a certain density structure or mineral assemblage, asking the code to produce it and looking at the density structure it produced to see if it's close to this. I don't know yet, but yeah, that's the idea.
I mean, you must know something about. I know no geology. Okay, so I'm coming from the other side. Is there speculation as to what kind of rocks you would have to form to get that higher density?
This layer is thought to sink in. there's debate on when this happened, while the magma ocean's cooling.
This is a model result,
Yes, this is a model.
but you don't know that it does that. But you're trying to get to, what is it, 3,400?
You mean the density?
Yeah.
This density structure is before this sinks in. I should probably show a different plot as well. Both these are after that dense layer has sunk into the interior. This density structure is before, and then the other is after.
Well, if I take the next one, if I take those and I integrate over the radius, it seems like there's a completely different mass involved. And there's just some overall constraint that just isn't balancing.
It doesn't go down to zero.
Okay, so all the models are going to go down and they're going to put really heavy stuff near the core.
Yeah.
Where that seismic analysis is saying that it's spread out more evenly.
At least
it's
in
correct.
The upper part of the moon. Yeah.
How should one think about the processes that affect the surface topography? You mentioned impacts as in volcanism.
Yeah.
And is there information in the surface topography, which of course is very well known, that's relevant to the cooling of the magma ocean?
One thing that people looked at is the dichotomy of the near side, far side, the topography of the near side being much lower. Some people have argued that's an original thing. It was as part of the cooling. One idea is that Earth's shine, so the Earth was hot at some point. The moon would have received that radiation. The near side would be hotter. Crustal thickness there would be less. That's one idea. I'm not sure about it because we're not sure how quickly the moon got away from the Earth. Probably fairly rapidly. It started around 3 Earth radii. So can you still radiate at 10 Earth radii and affect this cooling process? How that dichotomy happened. A model like this won't address it, but
In your models,
yes.
when you allow minerals to move between layers, are you going to allow for them to react with the melt in other layers,
Yes.
or will they?
Yes. It's a lot of computations. Every time you crystallize a series of minerals in all these layers, the code has to go, okay, this stuff needs to be here because it's where the density is neutrally buoyant. Now, once this material comes into this layer, it may not be chemically stable at that point. So it has to melt back into the liquid. You have to keep doing this over and over and over again.
Could we just go back to the slide? I was a bit confused with the ilmenite graph in the middle. Are there any data on that, or is that just...
Oh, so sorry. So the black line is from a MELTS model, and then the dotted red, they just simplified that to put it into this model.
the spike in density in the top there?
Yeah.
In the MELTS model, what mineral or mineral layer is that?
I think that's ilmenite. Is that wrong?
So that's actually in the model.
In MELTS, you mean?
Yeah.
I think so.
So when you're doing your redistribution, is there entrainment, or you move stuff from one layer to another layer? You do that. I mean,
It would be good to do that because then you get to the fractional and equilibrium crystallization. There's that debate. Yes, so if you did that, you could talk about that a little bit more and use that as a parameter that maybe you can dial up and dial down. It just makes it a little more complicated. So
Sort of conservation of mass problem when you're doing that? Is that what?
You know,
I mean, I'm taking your.
I'm thinking about it just in terms of that convective parameterization
Yeah.
of the atmosphere, right? You have a plume, but if you have an entraining plume, it behaves differently than a non-entraining plume.
You move stuff from this layer to that layer.
Is it going to mix with the liquids that are in that layer on the way up?
if there's a density difference, will all of it actually move to the new layer?
You're taking solids out.
Solids.
Solids are being
But the
not-
liquid has to mix
not
as well,
liquid.
right?
So it's solids that are being transported into a different layer.
Right. But the liquid has to mix as well because there's convection going on. It's hard. Yes, that's hard. Yes,
It's
that's
really hard
hard.
to know how to set it up.
It's named Tempe because of the place. I got my PhD at Arizona State, so Tempe, Arizona. It's because I wanted to do this years ago. It's been years of planning this and putting pieces together. It's a very complicated problem. There's a reason why people have highly simplified it, but I think this is the direction that needs to go. It's not just for the moon. Think about just generally thermal evolution of planets. You should be able to take some composition, a certain size of any planet, essentially, and then thermally evolve that. Ask the question, how long does that take? What's the composition? It's a much wider problem